Okay. So we had talked about equilibrium. The one thing I wanted to mention that I'm not sure was totally clear was that an object that's not moving is at equilibrium. But more than that, an object whose acceleration is 0 is not at equilibrium. Is there any case where an object is moving but has 0 acceleration? Yes. What is that? Constant velocity. If you can keep something at absolutely constant velocity, it's still at equilibrium. Therefore, it has 0 acceleration. Therefore, the forces are balanced. Up and down, or left and right, or north and south, or whatever your pair of opposite directions for force is. So that's just another thing to remember. Okay, so we're going to talk a little bit about Newton's 3. And Newton's third law is that equal and opposite reaction law. When you throw a ball, you pitch a softball, you throw a baseball, you exert a force on the ball. The ball exerts an equal force backward on you. These are action-reaction pairs, which you call what is kind of up to you, though we tend to be kind of us-centric, and we call the force that we're exerting the action force, and the force that the object exerts back on us the reaction force. If you've ever smacked something, hit a volleyball. Some of you have hit a lot of volleyballs in your life. If you've ever hit something hard enough that your hand stings, that's the force back on your hand. Years ago, I remember a very puzzled young man in physical science, when we used to teach it to sophomores, saying, well, then why don't I accelerate backwards? Why? It's a good question. But if we're talking about something on the x-axis, so here's you, throw a ball. Let's make the ball some other color that shows up. And you exert a force on the ball. Whoa, that's too big. That direction, and we're saying that the ball exerts a force on your hand that direction. The ball goes forward. Why don't you go sailing backwards?
A lot more mass than the ball.
Bingo. Because F equals ma. Your masses are not equal. So the forces are equal, but you are much less massive than the ball, therefore you don't accelerate at the same rate the ball does. You have really 0 acceleration typically, or what acceleration you have, you can counter. This is the idea of recoil. If you've ever fired like a shotgun or a rifle, I remember as a little kid, we had neighbors who were into the sort of mountain man reenactment stuff. They were back through the woods, and he had Tennessee long rifles. And for those of you who have not seen one, they're aptly named. I don't know how long the barrel is. I was a very little kid, and I just remember them being taller than me. And my dad really wanted to fire one of his long rifles, and we hiked back through the woods, and we went to visit. And I remember my dad, who was a relatively big guy, getting knocked backward by the recoil on this rifle. Because the bullet is moving forward with a force, and it's exerting a force backwards also. And so that's that idea of action-reaction pairs. When you hit a nail with a hammer, the hammer exerts a force downward on the nail exerts a force upward on the hammer. So we've kind of been doing this. We've been looking at pairs of forces all along. We just haven't put it in terms of Newton's third law. XKCD says, what happened? Where am I? Whoosh. Someone. There's no sound. Can't run, can't walk. It's in a bubble. Looks like physics professors don't like working in frictionless vacuums after all. They're such liars. This is funny because of all the problems. Like, why is this funny, Moser? It's funny because you know how we keep saying, well, we ignore air resistance. We can ignore friction. We pretend this isn't a vacuum, which is really convenient for high school physics and even some entry-level college physics. It's very unrealistic. So XKCD likes to poke fun at such things. Okay. So the way your book organizes this, I've mentioned, I hate. We already talked about this, because you have to talk about this before you get here in the book. So they introduce everyday forces in the third section of Chapter 4, which is dumb, because we've been dealing with gravity and normal force all along. So this is just sort of a recap of what we've already been talking about. Your weight is in newtons. Your mass is in kilograms, and pounds are just dumb. So Let's make that clear. Though I still can't, for the life of me, figure out how to order cheese in kilograms. Go to Canada, walk into a deli, and I'm like, I think about that much. So, weight is mass times gravity. This is how attractive you are to the earth. The more mass you put on, the more attractive you become. Many of us are more attractive after a December full of Christmas cookies. Much more attractive to the earth. And weight varies planet to planet. So you weigh less on the moon than you do on the earth, though your mass doesn't change. On Jupiter, you would weigh so much that you would be squished flat like a pancake. Your body would not. Oh yeah, the force of gravity on Jupiter is so high that your body is not evolved to withstand that. Your body, all of our bodies, evolved under this gravity. There are some really interesting questions about long-term space habitation so how many of you have elderly female relatives who have experienced any form of osteoporosis or pre-osteoporosis? Largely women, though men to a lesser extent. Bones tend to get brittle as we age, and one of the things they tell older women is weight-bearing exercise. Weight-bearing exercise, because your muscles are attached to your bones, and they exert force on your bones at those sites of attachment, and it actually helps preserve bone density. One of the questions about people living in space long-term or living on places like moon bases long-term is in reduced gravity, there is a tendency, because you're doing less weight-bearing, to lose bone density. So that's an issue. Weight is designated as F sub g. We talk about it as the force of gravity typically, and it's always directly down towards the center of the earth, no matter what kind of slope you're on. Normal force is in opposition to Fg from surfaces, and I think we've clarified this pretty well. Often equal in magnitude to gravity, or part of gravity. We could modify that, and we've talked about the cases where it's not just equal to gravity. So it's always perpendicular to the contact surface, and it only exists when there is a contact surface. Normal force is about to become even more important to you because it's going to be the key to figuring out the next force that we have. This is the next couple weeks of our lives. Friction opposes motion. Regardless of where that motion is happening, friction opposes it. Friction is the loyal opposition. If there's motion, friction is against it. Period. So, you have contrarians, what do you got? I'm against it. Well, that's friction. Friction is the ultimate contrarian. It is always against motion. So there are two kinds of friction that we're going to deal with. There's static friction and there's kinetic friction. Static means what? Being still, being the same, not dynamic. And static friction is at work when something is not moving yet. So I would like you all to stand up. And these chairs are fabulous. I want you to gently push on your chair in some direction, so gently that it does not move. Can you exert a force on that chair without moving it? Fortunately, our floors are really sticky, and these chairs have got rubber bottoms. They're also they've got that weird lever thing going on because they're cantilevered. But if you can push on the plastic part of the chair somehow, and it's not, just steady, we don't have to whack it repeatedly, just a nice steady force, but it's not moving, you're exerting a force on it. It's not moving because static friction is opposing your force. So, can you push a little harder and have it still not move? Well, you're pushing down. You got to push sideways. You're not going to beat the floor. Okay. Oh, fantastic, Logan. We're going to talk about what you're doing. So, I want you to experiment with gently pushing on it until it just starts to budge. There's going to come a point where it starts to budge. When it starts to budge, you have broken static friction. That is the point where you have overcome static friction, and you're now into the realm of kinetic friction. You didn't break the chair, you just broke fiction. Friction, not fiction. We can break fiction, I suppose, but you broke friction. So, how many of you have experience with pushing something around? Physically, anything that's not on wheels, a box, a laundry basket. This is how we move the laundry basket at my house because it's just unwieldy, so I kick it down the hall with my foot until I get to the top of the stairs. Does it take more force to get it moving or keep it moving? Get it moving. Once you got it moving, you want to keep it moving. You guys can sit down if you want to. Once, no? Okay, that's fine. You just have to go somewhere towards the back, so you're not blocking you make a better door than a window. Once you've got something moving, you want to keep it moving. If you've pushed something out of the snow, you know that once you get a little bit of motion, everything's smooth from there on out. So static friction is what's happening when the object isn't moving yet, but you're exerting a force on it. And it is, here, this is an easy one, and this is an always one. Static friction is equal to the opposite of the applied force. You can increase the applied force, and if it's still not moving, the static friction is still equal to it. Because if the thing's not moving, it's at what? Equilibrium. And if it's at equilibrium, acceleration equals 0. Now, at the point when you break static friction and it starts to move, now you're in the realm of kinetic friction. And kinetic friction retards motion. To retard means to slow down or to oppose, but it doesn't prevent it. Here's what happens. We get into the realm of kinetic friction, F sub k, once the applied force becomes greater than the maximum static friction between two objects. And for every object-surface pair, there is a coefficient of friction. We're about to talk about that. So if we're dealing with an axis where we only have applied force and kinetic friction, and it's at equilibrium, guess what? They're going to be equal. If it's not at equilibrium, we're back to sum of forces. And our sum of forces just got a little bit more complicated, which is okay. It's okay, I promise. So, general rule, static friction is bigger than kinetic friction. We said this, you know this intuitively. Once you've got it moving, the hard part is over. And friction is all about, it's actually about microscopic qualities of the surface, and you all, I'm sure, have that one friend who likes to do the whole, like, deep thinking, cosmic, no, dude, really, think about it. Okay. And, which is fine. That person has their place. It's good. It's good. But there's always, and I've had many students over the years, you could never really touch anything. Yes, dear, I know. Well, and it's the whole, no, because there are microscopic irregularities in all the surfaces, and when you think you're touching it, you're really not. Whoa. Yes, I know, dear. In the meantime, touch. But friction comes down to that relationship between those microscopic surface irregularities. So this is where, cosmic deep thinker person really has their forte, I guess. Every object surface pair has a coefficient of friction. Every single one of them. Metal on metal, metal on ceramic, metal on different kinds of wood, different types of wood surfaces, depending on which direction you're going across the grain, have different coefficients of friction. These floors with your shoes have a coefficient of friction, and it may not be the same for every pair of shoes you own. Coefficients, and this is where we get to use the symbol mu again. I love mu's. Mu. It looks like a U whose tail got caught in the door. Not tail, but front part. I'll shrink that. So long line up, and then a little U. So that's mu. And we have mu of static friction. That's the coefficient of static friction. Mu sub s. We also have mu sub k. Guess what that is? Not real creative here, folks. It's the coefficient of kinetic friction. So that coefficient of friction is a ratio. That's all it is. And it is a ratio, and this is something you will want to put on your note card. It is a ratio between the frictional force and the normal force. So the coefficient of static friction is equal to the maximum Fs max So the coefficient of static friction is equal to the maximum static friction. That is important because the maximum static friction is that point at which you break friction. It's the point at which an object breaks loose and starts to move, divided by normal force. And the coefficient of kinetic friction is equal to the kinetic friction divided by the normal force. And we can find kinetic friction pretty easily if something's at equilibrium, because we can look at net forces on the axis of motion. Can anybody start to see where these things would start to get complicated? So our little talk about sum of forces on Monday and pointing out that normal force is not always just opposite and equal to all of gravity. Slopes and ropes make normal force change, and therefore they complicate your calculations for coefficient of friction. But that's a little further down the road. So for right now, let's just be happy in the simple stuff. The simple calculations about coefficients of friction. Okay, so when basically what we have now is another variable. And so when we know mu, when we know a coefficient of friction, and we can figure out normal force, we can calculate frictional force. So we very often solve, and I notice that I'm using the generic F sub F here, which is generic frictional force, because I'm talking about both static and kinetic, and there's no subscript on the mu for the same reason. Because here, this is applicable to either static friction or kinetic friction. So let's go ahead and we're going to do the 4C practice problem, and then we'll turn you loose. So, 4C, we've got a 24 kilogram crate. It's at rest on a horizontal floor. Oh, thank goodness, because we really hate slopes here. And it requires a 75 Newton horizontal force to set it in motion. Find the coefficient of static friction between the crate and the floor. So, what are we given? Well, we're given the mass, 24 kilograms. We know that Fg will equal mass gravity. We are given the force of static friction max. We are? Where do we get the force of static friction max? It's the force that's required to break friction. So 75 newtons is the maximum force of static friction. And what we want is mu s. So in order to do this, we got to start with the free body diagram. We got to label everything. So what's our first force on this object? Gravity. Everybody loves some gravity. F sub g. What other forces do we have? Normal force. Everybody loves some normal force. So what this means is that the negative force applied is equal to the force of static friction. Okay? Reasonable? Logical? Sensible? Okay. That means we can take this and put it in there. Okay. So now this is really easy. Mu s equals the negative of 75 newtons over the negative of 24 kilograms, 9.-81 meters per second squared. And this, of course, ends up being in newtons. Okay. So we get a mu s of 0.318552497. That's a pretty standard kind of coefficient of friction. What are our units? So do dimensional analysis on this part. Newtons divided by newtons gives you what? Nothing. What are the units on ratios? Nothing. Units, ratios are unitless. A ratio is by definition unitless. So the coefficient of friction, and I find myself like doing that all the time. 'Cause I'm like, where are the units? Oh, it's a ratio. Where are they? It's a ratio. You'll probably do the same thing. So ratios are always unitless. So the raw answer that we get is 0.31855, etc. We have 2 sig figs to work with. For once your book's sig figs and rounding are correct, we would say that mu s is 0.32. And usually our little ratios are under 1. I'd have to think of a case where the coefficient of static friction was over 1 for something. But that's fairly standard. Okay, so assigned are the 4C problems on page 145. Okay, all of them. 1 through 3, but there are multiple parts. So coefficients of friction are given as positive numbers. We kind of ignore the sign on that. This is one of those things where, the way your book handles gravity is they make gravity 9.81 meters per second squared, and they drop the negative, and you have to account for negative g. I've never done that. And in this case, there we go. It's one of those where it throws a little hitch in the get up. So we're kind of ignoring sign on the coefficients. It should always be positive, yes. Your coefficients should be positive. So in talking about this, coefficients of friction are positive. If you had a negative coefficient of friction, it would mean that friction actually sped things up as they moved. And we know that doesn't happen. This comes out of handling of signs. Note that your book shortcuts all that and just takes the magnitude of the force of static friction and the force of gravity. They don't do the sum of forces. So they sort of are less legalistic and less proofy about it. I don't have a better answer than that, other than to say that, yes, coefficients of friction are always positive, so we're taking the absolute value of that. I guess it gets worse and trickier when we get into 4D. So for now, if you're okay with it, and I know some of you are awesome, wonderful, deep, I need depth kind of answer kind of folks, which I appreciate tremendously, but I don't have a better answer. So I'm just going to have to leave you peering over the edge of that cliff. So if you can live with the fact that coefficients of friction are just positive, just live with it. I don't usually say things like that, but I have to here. I'm sorry. Can I talk about how this gets muddy? So, Logan, when you were pushing on your chair, I noticed that you were exerting your force. And I'm going to draw you. The reason I have this up here, so the case that we just did is this. Logan is pushing evenly on this box, or whoever this is, and that means that the force applied to this box is directly horizontal. Just a little delayed. So this is easy. We did a sum of forces, but we really didn't have to. We could mentally account for the fact that force of static friction max was equal to applied force. When you were pushing on your chair, so I'm picking on you because I noticed that you were pushing down really hard, the force that you're applying is now down like that. Okay, so when we're looking at a frictional force, when you're pushing on an object, intuitively, you know that if you want most of your applied force to be going to moving the object, which one of these is the optimal pushing position? Middle. Because all of your applied force is on the axis where you're getting the motion going. If you're in this top position where you're actually pushing down on the object, you're adding to gravitational force. What are you in fact doing? Increasing your normal force, because normal force is now overcoming that additional force downward on the y-axis. You can do a sum of forces to prove that to yourself. If you're pushing upward, what are you doing to your normal force? You're actually decreasing it, because you're pushing against gravity. You're adding a force on the y-axis in the up direction. These things will change the apparent, they will change the frictional force. They will not, however, change the coefficient of friction. And we'll do a lot more with that probably next week. I think we'll probably do the box of your favorite things on a rope around the school to figure out coefficients of friction. In the meantime, go ahead and start on the problems on 135, but I just wanted to plant that seed sort of intellectually.
A literal